I didn't mean the videos that I posted for class last week. I meant the in-class videos. Anybody watch the in-class videos from before?
Can't briefly watch one.
Can you hear me? Yeah. Okay. So I don't know how the iPad mic works if they're longer than a room, but all right. That said, it is what it is, I suppose. So where are we? This is the last day of class. Yay. Should be happy about that, I suppose. We made it through a semester of circuits. Or almost made it through. Things that wrap up the semester, we do have some homework due tomorrow, so that's stuff to look forward to. So I can give you homework over the summer too if you're gonna miss doing things like circuits. Just to keep it going. Where else? The lab is due tomorrow. Did I post the lab submission? Lab's due. The what?
The homework submission?
The homework submission is not posted?
Yes.
All right, I'll try to do that. But the lab submission is posted. And then the excitement, of course, is Friday we get to take our final. So, I did post a note on Brightspace with the details there. It's a short note, just tells us what time the final is and where it is. You will get all fourth grade sheets, so you'll have that available to you. And make sure you bring a working calculator. So probably have to crunch some numbers. It's a good idea to have something that can crunch numbers. Bring a backup, I suppose, if you need. That said, that's about for administrative stuff. So our class will end on Friday. Anybody have any questions? Yeah? How was my semester? I had motivational problems this semester, I'll admit, so I've had better semesters. Nothing to do with you guys. Some personal stuff going on in my life. So. I suppose on that same note, at the end of the semester, I just found out this morning that I need about $10,000 of dental work, so get that going for me. So there goes all my spending money for the year. So yes, I've had better semesters, but thank you for asking. It's kind to ask. How about you? Good semester? Yeah. Anybody else have any questions? I suppose personal or class related. Or specifically, I suppose, in context of your final class related would be more pertinent. No one has any questions on any material? With the final in 1, 2, 3, 4 days from now? Yeah.
Will the office hours on Wednesday just, well,
Oh, that's a good question. No, I will not be here on campus. I will be in my downtown office all week. So I guess technically my official semester office hours ended this morning. And so for the rest of the week, I will be in my office at the downtown campus. And I'll be there pretty much every day. Yeah. Yeah.
it's not the only kid's solution for the exam, only one solution.
Yeah, instead of question of time, by the time students ask me for a solution, I just don't have time to write one. So I don't usually write solutions to the test for myself. I do it as a courtesy to you when I think about it. So I don't write up a formal solution to the test, I don't do one. So I only do it as a study aid. I mean, I've had this conversation in class before. I think having a solution posted is a distraction more than it is a help. Because as soon as you get stuck on something, you just look at the solution rather than try to figure it out. I mean, I'm not saying you, I should include myself, we tend to do path of least resistance type of approach. So it's much better to figure something out than to get stuck and then, throw in the towel after 30 seconds and look and say, that's who did it. Yeah.
How's the ECE and showcase, ECE project? Do you think they have to showcase?
Do I think the projects were good?
Yeah, ECE.
I only looked at the senior projects, so I didn't have time. I was one of the judges, so I didn't have time to go look at projects were pretty good. There's nothing that, I mean, some of them, this is true always, and you'll find this in your personal experience, some of them could have gone much further. And part of that's an efficiency thing, and part of that's a willingness to get up and build things and then break it. That's one of the most significant things that I've noticed among your generation versus my generation is, kind of that willingness to get in and get your hands dirty, that, I kind of grew up building stuff, like I'd go to Radio Shack, which is now bankrupt, of course, and buy a transistor radio kit. And so I could build a circuit when I was like 10 years old. No one's gonna try and build a phone. So it's just not possible. So you're a little bit more removed from electrical engineering, I think, which makes students a little bit more hesitant to actually start things. Which is not true for everybody, there's a Gaussian curve here, so, but I find, over the years that students are more and more nervous about trying to build something. And the exciting things that happen are usually when things burn out, so that's fun. And I've had students that got quite nervous until they realized that I thought it was funny. So, you kind of, the one thing that I wish I could stress more is just try to build something. And then once it doesn't do what you want, figure out why, fix it, make it better. That's what engineering is. So, you know, crossing that threshold, that willingness to, you know, just get in there and start putting things together. I mean, there's certainly safety protocols, like you never use power equipment. Don't just put your, you know, go down at a table saw without some training on it. So, don't do that. Yeah, so try, build stuff over the summer. Burn out some electronics. Electronics, well, the right electronics is cheap. Don't burn out expensive electronics. It's gonna happen anyway, but it's better to burn out the 5-cent part than the $500 part. At some point, we'll burn out the $500 part too. It's gonna happen. Yeah.
What do you think about the guy who was turning light into Wi-Fi?
Oh, I like that project. That's the project they want.
Was it?
Yeah,
Wait, which one is it from?
the Wi-Fi project.
Wi-Fi?
Yeah, the Wi-Fi. No, they did a good job. I thought they did a good job. And it looked, I mean, they took their prototype to a presentable prototype too, which was, I mean, impressive. Like, if you looked at it, it looked clean. Which is one of the things that matters in engineering. So in other places, like for first robotics, one of the criteria for judging if there's like wires all over the place and they're not, you know, neatly organized, the teams get marked in. So their cleanness of their presentation was I thought it was a big plus. And Wi-Fi is something that people care about a lot, so it was a very relevant project too. Did you like it?
Oh, yeah, it was sick. I'm standing on it.
And the fact that it worked, I mean, they were transmitting binary by LEDs that were blinking, what was it, 200 kilohertz or something like that? Somewhere around there.
There were a lot of like safe boxes in the showcase.
A lot of,
Like,
that's
there
because
was a lot of safety boxes.
the junior pre-capstone, that was their assignment.
Yeah, but like I saw like 3 of them. Like one of them.
There was about 18,
There was 18 there.
I think,
There
or
was
15 or something.
it has to deal with like the prevention of theft packaging, package stuff.
That was the project they were assigned. So the entire class had to do the same project.
Also, yeah, I see a lot of them. One of them even had like they made like a website or made a website for where you want your package.
And if you were at the presentation there, that was the team that won.
Wait, the one with the website?
Yeah.
Oh, so they that was actually like the
I didn't go see it, so unfortunately.
I did saw you over there, right?
I saw most of you, and I made a note. Yeah?
What did you think of the, when they did like a demo of like the traffic box, like that helped prepare, like.
That was good too. Yeah, I thought these are, the underside, so when they talk about neatness,
Yeah.
if they lifted it up, that
They
was,
showed me
they should clean that up.
the bottom of the.
So, I get chastised them a little bit for, not doing that. But they, clearly put some time in, they were good at answering questions. That was an important thing as well. So the Wi-Fi people, answered questions very well. So knew their project. That's an important thing.
I was interested in creating like an electric bike, like something, I don't have one, I think that's a good project.
What do I think is a good project?
Right?
There's lots of them. If you wanna talk to me, downtown campus, I have lots of projects that I've been doing work on.
So there was one that has like a little bit more movement, that kind of like, I felt like I kind of have like interest in.
Yeah.
It was the one with the wind currents, like, you know how like there's like these like boats like in like the middle of like oceans and like
Oh, yeah.
testify of wind currents and
Right. That's an ongoing project sponsored by the
sometimes they,
Atmospheric
like-
Science Department.
you're trying to prevent like anyone trying to replace those every time because those are like.
No, they were trying to compensate for sensor readings.
That's actually, that one kind of like, because that one was like the only one that I remember that like
Yeah.
has any movement in, that has any movement. Like besides.
Well, it's a mechanical
Yeah,
system,
it's a
fluid
mechanical.
dynamic system.
Mhm.
I'm glad you enjoyed, those of you that went, enjoyed walking around, seeing the projects. I'll have to share with Dr. Muckle that he made those observations, he's the capstone professor. Anybody watch the line followers? There was some cheering going on there.
The basic one, that's
From 111, yeah. But I didn't get to go over and see, all I heard every now and then was a big cheer going up as I suppose the car completed the course, which was pretty cool. So it was nice to see students involved. Excited, cheering people on. Nobody has any technical questions? I mean, again, we have a Sylvester's worth of work coming up on Friday. I do have new content, but yeah.
So it's gonna be like every single thing, right? Like including.
It's comprehensive, right. 1, 2, 3, obviously, I suppose I should emphasize this, the majority of the tests will be on unit 4. Yeah,
We'll stop that, not previous pictures we got of Transformers.
everything that we have homework on is very good. Yeah, there's, I guess, with the way our test block works, they can't give you every single problem, every single concept, there's just not quite enough.
Transformers gonna be part of the test.
Anything you have homework on?
Also, I noticed you were trying to submit a homework 26, and it was kind of deleted.
No, someone just, I never deleted it, I guess I just forgot to post it. I'll do it after class.
It's already bad, it's already the end of the, like tomorrow's the last day of.
Friday's the last day. Well, tomorrow's the last.
Tomorrow's the last day of classes, so
Well, you had all weekend to do the homework, you already finished it.
we have to study.
That's what homework is, it's study.
We gotta study. Don't put that up. We have like a while to.
If you can do homework 26 well, then you have a very good command of all the unit 4 material. There's a good synopsis for unit 4. At least for second order systems, first order systems are easier. Yeah.
For tomorrow, were you being serious or joking that you're still gonna be there tomorrow, or is like lab just canceled?
I'll be here. I mean, if anybody needs to collect more data, I can hold the lab as open shop. Does anybody need more for, or is the lab?
That's more as like coming in the act, like more like text, like.
I'll be around if you wanna ask questions, sure. I'll probably go running as long as it's not too rainy. So I'll be gone for about an hour. Any other questions? All right. So I do want to talk about new stuff. This is a continuation of our Unit 4 material and a nice segue into those of you who are going to take signals. Not that I expect everybody to remember this for the next few months, but we should see it. So our method of solving initial value problems involves finding our differential equation and then depending on the order, first order, second order, looking at our homogeneous and particular solution and all that stuff. There was our methodology. There is a Laplace approach. To solving initial value problems. Transient problems. And I'll do what I tend to done in the past. I kind of provide us the detailed steps. So our first step is a familiar one. Draw the circuit. In the S domain with impedances. ZR, ZL, ZC, we're very familiar with those, so there's nothing new here. The next step will be new, though. Determine the Laplace transform of the source. This is not something we've done before. And I'm going to pause for a moment in our steps. So, for example, what's that? Determine the Laplace transform of our source. So, for example, one of the sources that we've studied extensively this semester is our step function source. Everybody should be familiar with that. We know that's the source that turns on at t equals 0. So, Laplace transforms. An example, step function source. V of t, Vs of t, I suppose, equals 5 u of t. So we should recognize that that's 0 volts for t less than 0 and 5 volts for t greater than 0. Familiar step function expression there. But if we're going to use Laplace analysis to determine our transient solutions, we need to take the Laplace transform of that. So we have cursive L of both sides. Actually, we don't need it quite like that. I'm going to redo that, sorry. And just say Vs of S is the Laplace transform of 5 u of t. And 5, as we said before, is a constant. We can bring constants out front when we do Laplace transform and distribute the property. It's not part of our math per se. If we look at our Laplace integral expression, I suppose I can ask, by this point in the semester in your diff EQ class, did you see the Laplace integral expression? So it is familiar, so I don't have to talk about it anymore. With that said, here's our expression when we bring that 5 out, and we have the Laplace transform of u of t. Now, we can go use that Laplace integral expression and find out what the Laplace transform of this is if you're interested. I'm not interested. So I'm glad the math department has had that discussion. What I care about is using the Laplace table. So here is a table of Laplace, and I suppose if you want to think about it, inverse Laplace transforms. So the left side of our table is just functions of time. The right table is the equivalent expression in the S number. It's a lookup table. So there's nothing huge or revolutionary about it. We can look. So all of our time expressions on the left side, left column, there's two columns, but the left side of each column. All our time expressions are valid for t greater than 0. The assumption, as I've said before, is that our functions are 0 for t less than 0. So technically, even though I don't like the way this is written, this is the step function right here. This is equivalently u of t, because it's t equals 0, or t equals 1 for t greater than 0. Everything here, we can say our functions of time equal 0 for t less than 0, which makes this u of t. I've always tried to remind myself to find a different Laplace table. This is the one that almost always comes out first in Google when I look for Laplace tables. So it's kind of my go-to table. I've been using it for a number of years, but just to point that out. So that said, if I take the Laplace transform of u of t, it's 1 over s. It's a solved problem. You could go do the integral expression. Integral of the st from 0 to infinity, or whatever it was. I don't think I have that quite right in my head, but you could go do what they taught you in IFEQ, find out what the Laplace transform is. I don't care. Don't do that on the test. It's not what we're using. If I were to give you extensive Laplace transforms, I would give you a table that looked like this, usually a more pared down one. And again, all these functions are u of t functions, so there's a sinusoid that starts at t equals 0. That was part of our discussion in the videos, if you watched them for last week when we were in this class. And we can take the Laplace transform of the sinusoid that turns on at t equals 0. As I said in that video, that's a very common thing, because anytime we plug stuff into the wall, it's a sinusoidal signal. And there's no signal until we throw the switch and turn it on. But then it's a sinusoid, and we could ask the question, how does it behave for t greater than 0? Here is the Laplace transform for that sinusoidal function, and then the cosine function as well over here. Between the two of them, we can get phase. And so there's a lot of much more complicated functions. There is one off number 2 there that's pertinent. So one of the things, again, that I would like to do, a little hard to read, I'm going to zoom in there. That's e to the alpha t. I can recognize I could write this as e to the, or minus at, I should say. And then if I put a minus sign there, then that just makes this 1 over s plus a. So there is our Laplace transform for e to the minus at. And again, you could go do the integral expression, crunch that, prove that to yourself. But that's also a fairly common one, so fairly important. The powers of t, sometimes I've done that just for kicks and giggles, but a lot of these are a little bit more complicated than we care about in class. And so there's an exponentially decay one. So again, if I could put the minus sign in, minus at sine bt. If you think about that, that looks a little bit like one of the terms we see for our underdamped homogeneous expression. E to the minus alpha t, and there we have a sine and a cosine, cosine beta t plus sine beta t with our coefficients and all that. But it is a comparable thing, a little bit more complex algebraically, but here it is in the Laplace table. And then down here at 23, we actually see our critically damped case. So if n is 1, we have t e to the at, or again, related a little bit more to the critically damped, our second term, e to the minus at. And our Laplace transform there, if n is 1, we have 1 over s plus a squared. So it's a very mathy looking table, but it is, again, a plug and chug thing. So things that we recognize on there, maybe not right away, but they are there. I suppose if you're familiar, 17 is hyperbolic sine. It's starting to get a little bit esoteric in a lot of settings. There are some other features here that would be useful if we had another couple weeks of class, like this T minus C type of thing. One thing we do see that's a little bit familiar is there's the derivative, df. I don't tend to write the prime form of the derivatives, I tend to write df by dt. And there we see that's multiplication by s in the Laplace domain. So that was the conversation we had before. There is another term there, but again, if we had a little bit more time in class, I would talk about that other term. That's an initial condition term, and so Laplace can get a little bit more sophisticated. And here we can look at second derivatives. So if n is 2, the second derivative of f with respect to time is s squared times f. And that's again something that we're fairly familiar with. So there are things we see here. That said, I'm going to concentrate on our step function there at the top. You know, again, as before, keep things fairly simple. And even though they're simple, it's still not unrealistic. I tried to emphasize that point. As we looked at step functions for DC problems, step function responses are very common for digital circuit analysis. So we just need to take the Laplace transform of this to finish out our example, and it turns out our Laplace transform is 5 times 1 over s, or 5 times s. And I suppose I should change my 5. So it has happened before. Someone else mentioned this as well. My 5s and my s's tend to look the same, so I'm just doing this for cosmetic reasons, so that we don't have confusions between 5s and s's. And I usually try to remember that when I do the policy analysis here. Just I suppose I really like 5. But that said, there's our Laplace transform of a source example. We'll run with this example in just a second. So going back to our steps, determine the Laplace transform of our source, draw the circuit, so to speak. So both step 1 and step 2 are drawing the circuit. And step 3 is a familiar step as well. Use circuit analysis to determine the Laplace expression for our parameter of interest. So voltage across the resistor, voltage across the capacitor, whatever it is we're interested in. So, and that's something we've had to do before, but now what's a little bit different here is we have a function for our source. It's not an arbitrary source, it's a mathematical expression in the Laplace domain. That is a fundamental difference. So when we were doing our differential equations, it was just some d out of s. I had no idea what the expression was when we did Laplace, inverse Laplace transform. Now I specifically know what my mathematical expression is. Our next step is use partial fraction expansion. To simplify our expression. Specifically, to simplify the denominator of our expression. And so, one of the things I have noticed over the years, and I'm curious why this is, but it seems like students are more familiar with partial fraction expansion than when I first started teaching circuits. Is everybody pretty comfortable with partial fraction expansion? Just to check. Yeah, I kind of wondered what's changed in that educational system if that's the case. Because when I first started teaching, there were a lot of students that were unfamiliar. Anybody not familiar? It's a big no. 5, apply the inverse Laplace transform. The inverse, left off an important word. To determine our transient response. So we're going to go back to an old friend, our RC circuit, and apply this methodology. So there's our last step. So, to do an example, we'll make that 10 u of t just to use the value we've already looked at, some R and C, and just to be familiar, there's our RC circuit that we've studied so often over the course of the semester. So, familiar problem, we know how to do this transient analysis using differential equation, find the homogeneous solution, find the particular solution, and all that methodology that hopefully everybody's very comfortable with and can demonstrate on the final on Friday. That said, our step 1, we have a ZR, which is 1K. We have a ZC, which is 1 over SC. And we can write that as 10 to the 6 over S. Or 1 over S times 10 to the minus 6, however you prefer to write it. I didn't give us an output, and I'll do that in just a second. And then we have our Laplace transform of our source. I mean, we can rewrite that. We've already kind of done the heavy lifting there. We know Laplace transform of 10 u of t equals 10 over S. So that was on our previous page. And we can write, doesn't matter whether that I write it as a DC source or an AC source. There's our Laplace transform of our source. So that's new. That's the point to emphasize. This is a new thing where we know in the S domain exactly what our source is. So, all right. Well, let's be a little bit different. We'll come back to the capacitor later, but let's find the R of t. Let's make that our goal. So hopefully we all recognize, our step, this is step 1 and 2, I suppose. Our step 3 is use our circuit analysis. And the circuit analysis approach that I would tend to use here is voltage divider. It's 2 impedances in series. Let's use the voltage divider circuit. It's very, very useful and relatively straightforward and all that. So we know the R of S is ZR over ZR plus ZC times VS of S. But we have expressions for all that, so just writing it symbolically to set it up. And so we get 10 to the 3 over 10 to the 3 plus 10 to the 6 over S times 10 over S. So again, that part's new. We have completely represented everything in the circuit in the Laplace domain, including the known mathematical expression for the source. We do want to clean things up a little bit, however we want to approach it, perfectly fine. Equals 10 to the 4, where S times 10 to the 3 plus 10 to the 6. And divide through by 10 to the 3, we get 10 over S plus 10 to the 3. I could say we're going to apply partial fraction expansion to that, but there's no expansion to do. It's just a single term, first order expression, I suppose. So we can write VR of S, Here's our step 3. Our step 4, not needed. We will use it shortly. So, not needed. Step 5 is take the inverse Laplace transform. So VR of t is the inverse Laplace transform, Laplace minus 1 of VR of s, but we know VR of s. We just wrote it on the previous page. It's 10 over s plus 10 to the 3. Does everyone agree? I haven't asked that yet. Everybody comfortable? Questions? You look unsure. Are you sure? Good. So anyway, once again, 10 is a constant, so we can factor that out. Equals 10, Laplace minus 1 over s plus 10 to the 3. Well, now we want to visit our friendly Laplace table. And we've actually already looked at this one. So we have 1 over s plus some constant. And go back to our Laplace table. And look at the one that I wrote up in the upper right corner there, number 2. 1 over s plus some constant is e to the minus that constant times t. And just looking it up on the table, finding that parameter. In fact, in the original document, it's written as 1 over s minus a. That's fine. We can say minus a equals 10 to the 3. And then a equals minus 10 to the 3 if we want to plug that in. However you want to represent it. But there is our Laplace expression. From the table, we get equals 10 times e to the minus 10 to the 3t equals, of course, 10, just factoring out, minus 10 to the 3t. For 0 less than t. So we did all that in Laplace. There's our voltage as a function of time. We should check it using things that we know, but we didn't have to do any initial value condition stuff, all that particular solution stuff that we had to do. All of that's not part of this analysis. We just used the mathematical estimating and inverse Laplace transform back into the time domain. That said, let's check our work. So there are 2 things we can check, based on previous principles. One, we can look at our initial condition. So, and 2, we can look at the t goes to infinity circuit. So here's our original circuit, and hopefully we can kind of do this by inspection. What is this value as t goes to infinity? What is the resistor voltage as t goes to infinity? What's that? Not quite. What happens as this argument gets really, really big? What is e to the minus a really big thing do? Goes to 0. So mathematically, you can plug in. If you don't know, plug in e to the minus 1 million. Plug in a number, check, see what it does. But e to the minus something is an exponentially decaying thing. So as time goes on, we expect it to go to 0. It's something we want to recognize. And it comes up a lot. It's a very important mathematical expression for engineering. So this goes to 0 as time goes to infinity. Let's check with what we know about the circuits. I could draw the process, but we should be able to do this kind of by looking at it. As time goes to infinity, what happens to the capacitor? We already know the answer to this. It's an open circuit. Remember? So what do we reach? As time goes to infinity, our circuit reaches what? Concept that I've said multiple times. You said. Yeah.
DC steady state.
We reach DC steady state. So at DC, caps are open circuits. and inductors are short circuits. No inductor here, so you don't have to worry about that. But caps are open circuit. So if cap's an open circuit, as time goes to infinity, what's our resistor voltage then? Zero, because no current. It's a series circuit, no current to an open circuit, no current, Ohm's law, then V equals IR, if I is zero, V is also zero. That checks with our answer. So this is always a good thing to do, is to look at our mathematical expression and quickly just say, does it check with what we expect? And this is something I've qualitatively brought up before. I have had students in a test situation give me an answer and write down, I know this is wrong because. And I always give them more credit than if they just wrote down the answer. Because if you know your answer is wrong and why it's wrong, I mean, that's what engineering is all about. I mean, that's the process. In a test setting, that's a little bit stressful, so usually you want to correct it. But time permitting, if you just say this is wrong because blah, 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 then usually I give you more partial credit. In this case, we're not wrong. What's our other check? We can check as time goes to infinity, we can check at t equals 0 as well. What's our capacitor voltage at t equals 0? Is it? What's your capacitor voltage at t equals 0 minus? 0. Why? There's no source. Everything's off. T equals 0 minus, capacitor voltage is 0, which means the capacitor voltage at t equals 0 plus is what? Still 0. Which means KVL gives us what voltage across our resistor at t equals 0? 10. So 10 equals VR plus VC at t equals 0 plus. I should be more specific. But if VC is 0, the voltage across the resistor has to be 0. There's a quick check we can look at. Is that accurate? Is our voltage at t equals 0 plus 0? Hopefully we all agree yes. We plug in either 0, we get 1 times 10 is 10. There's our check. You can always, within some limits, we can always look at our mathematical expression and see if it matches physical expectations. I mean, that's ultimately what this represents, is the physical characteristic of the voltage across the resistor. And we know qualitatively how things behave in this circuit for a step function source. So that said, all right, let's just take things to the next step and do a little bit more work. Let's copy this entire page, actually. And let's look at the voltage across the capacitor. You're in my way. VC of t is our parameter of interest now. And in this circuit, it's VC of S. And so it's still a voltage divider circuit. We're familiar with this. We've done it a lot of times before. We can even take some shortcuts and write down VC of S is 10 to the 3 over S plus 10 to the 3 times 10 over S. There's our Laplace transform of the source. And then there's our voltage divider. So that was essentially steps 1, 2, and 3. So there's step 3. I skipped the math for it like I'd done before, but we've done it often enough that hopefully you're comfortable with that. What's that?
When did you change before? Can you go back?
It's the capacitor voltage we're looking at now.
Oh, it's
Yeah. We're looking at the capacitor voltage. Now, there is no Laplace transform for this circuit. We have to do step 4, that we talked about a few minutes ago. We have to do the partial fraction expansion. I will show you my method just for I guess historic reasons. But partial fraction expansion, we take our factor denominator, so s plus 10 to the 3, and s are two factor terms in our denominator, and we find the coefficient coinciding to each of those. I'm sure that you have a methodology. I'm going to just do mine for kicks and giggles. Finding the coefficients. For partial fraction expansion. So, for each denominator term, evaluate the expression at the pole. And then determine the coefficient. The associated unknown coefficient. I suppose I'm going to add another step at the first. Add a little bit more. Call that 2 and 3. Multiply both sides by the denominator term. Just to clean it up a little bit mathematically. That way you don't have to worry about singular expressions. So that said, it's hot. Is it hot or is it? What's that? Seems normal. Everybody good? So, we have, what did we have? 10 to the 4 over s plus 10 to the 3 times s equals some a1 over s plus 10 to the 3 plus a2 over s, or either way, however you want to write it. There's our fundamental expression. You can copy that. And finding a1. So I'm going to multiply both sides by s plus 10 to the 3. As long as I do the same thing on both sides, it doesn't matter what I do. And I get 10 to the 4 over s equals a1 plus a2 s plus 10 to the 3 over s. So there's our step 1. Our step 2 is I'm going to evaluate the expression in our pole. And our pole is minus 10 to the 3 for the s plus 10 to the 3 term. So we have two poles, we know this, 0 and 10 to the minus 3. Pole is a loose word. It's not really a pole because that's not exactly a transfer function. So I'm playing fast and loose with some terminology, but I'm gonna evaluate at minus 10 to the 3. Arguably, you could say the roots of the denominator. Evaluate the root of the denominator. So in this case, minus 10 to the 3. So I'll plug that in.
Wait.
10 to the 4 over minus 10 to the 3, not plus, equals some A1 plus some A2 minus 10 to the 3 plus 10 to the 3, which hopefully we recognize is 0. That term goes away, and we're left with A1 equals minus 10. Do we agree? Check my math. Always check my math. Too much math in my head.
Is that another 10 over 3?
I don't know what you're talking about.
There's two 10 over 3s, there's like negative 10 over 3 plus a 10 over 3. On the third part,
Okay.
the one that you crossed out to 0.
I'm evaluating an S equals minus 10 to the 3. So wherever there was an S, I plugged in a minus 10 to the 3. So there's our little process. We can continue just for the other term. Finding A2, same process. And again, in my experience, I think students are learning partial fraction expansion a little bit differently, and that's fine. I don't care personally how you determine the coefficients. I'm not emotionally invested. Multiply by S, there's our step 1. We get 10 to the 4, S times S, S over S cancels. I suppose I should point that out. Equals S, A1, S over S plus 10 to the 3. Plus A2, and then we're going to evaluate this at S equals 0. Again, the root of our denominator, the other root of our denominator expression. So we plug in S equals 0, we get 10 to the 4 over 10 to the 3. Equals some A1, 0 over 0 plus 10 to the 3, but we do recognize that vanishes once again. 0 goes away, no contribution from A1. And so we get A2 equals 10 to the 4 over 10 to the 3, which is 10. A2 equals 10. So, all told, we can write out our expression, VC of S is minus 10 over S plus 10 to the 3 plus 10 over S. There's our partial fraction expansion, and if you want to get there some other way, sounds cool. Now we can take the inverse Laplace of that. Laplace minus 1. The right side is just VC of t. That's what we're looking at. And then the inverse Laplace of minus 10 over S plus 10 to the 3 plus inverse Laplace of 10 over S. But once again, that 10 in the numerator is a coefficient, constant. You can factor it out. Bring it out of our inverse Laplace, it does not contribute mathematically. So we can write minus 10 times inverse Laplace of a familiar expression plus 10 inverse Laplace of 1 over S, which is also familiar. Once again, if we do this often enough, we know off the top of our head, we can go look at our Laplace table for both of these. We'll flip back and just point them out once again. So there's our 1 over s plus some constant. And we know that's e to the minus at when we do the Laplace transform. And then we have 1 over s here. Zoom in a little bit. And the Laplace transform of 1 over s is the step function, but mathematically inverse Laplace transform of 1 over s is the step function. But for t greater than 0, it's 1. And all our solutions are for t greater than 0. You know, we said that before, but they emphasize that point. So we don't have to write the step function. We just know our solutions are valid only for t greater than 0. And so we can go back. And write minus 10 e to the minus 10 to the 3t plus 10, I suppose, volts. There's our capacitor voltage as a function of time. We can do a quick check. Once again, as time goes to infinity, what happens to this term? What does happen to this term? It goes to 0. I mean, there's another reason we can say that. I mean, mathematically, again, we talked about this. We should recognize that exponential arguments go to 0. This is the homogeneous expression. We talked about that before. And the homogeneous terms always vanish as time goes on. And then we're just left with the particular solutions. The definition of our kind of very basic differential equation response is our homogeneous terms always vanish until something changes in the circuit. Physical change, parameter change, voltage changes, component changes, whatever. Homogeneous expressions always vanish with time. And so if we wait long enough, this goes to 0, as you all said. We're left with 10 volts, and that's consistent with what we said before. I mean, I could bring up our RC circuit. We reach DC steady state, capacitor's open, EDL tells us that VR is 0, meaning or indicating DC equals Vs, which is 10 volts for t greater than 0. We wait long enough. Likewise, our initial condition for the capacitor voltage was 0. We had that discussion. Does that check? So we plug in t equals 0, what do we get? Minus 10 plus 10, which hopefully we all agree is 0. Questions? Yeah.
So you said the homogeneous term will vanish. Is it just for capacitor?
No, always. It doesn't, any mathematical expression, doesn't matter, mechanical engineering, chemical engineering, whatever. Any solution for a simple differential equation, ordinary differential equation, the homogeneous terms always vanish for initial value problems. There are more sophisticated differential equations where that's not the case. So if we have a feedback system, in which case, so one of the things I tend to call this is, well, 1 over 10 to the 3 is the time constant. I tend to also call this for second order systems the attenuation constant. In second order systems, we also look at damping. But there can be positive feedback in the system, and if there is positive feedback rather than minus 10 to the 3, we would have plus 10 to the 3. So in order to do that, then we need an active component. By active component, I mean something like an amplifier. So for passive circuits, this is, I suppose, we're spending the noon on because you'll hear this term not infrequently. Resistors, inductors, and capacitors are always passive components. They don't have any active elements themselves. They are not powered. Most active elements have a power supply associated with them. So any combination of resistors, inductors, and capacitors is a passive circuit. So a little bit of terminology to get into the good engineering parties. Yeah.
Just make it sure, you don't have to say 10U or T, right?
Usually, and if you notice my solutions, I usually, if I remember to, write valid for 0 greater than t, which implies U of T. I mean, mathematically, I could put brackets around all this. I'd have to put brackets around everything, that's important. And then put append a U of T there. So that is the equivalent thing. So it's a subtle but interesting point, I suppose. So I could do this and say U of T. And that's the same thing as writing that. So we have, again, no knowledge, even though this is only quasi-true, of course, we have no knowledge of what's going on before T is greater than, or T is less than 0. We don't know what was going on with the circuit. I mean, that's obviously not true. We know the circuit was off or whatever. But it's not part of our mathematical response. Our mathematical analysis is only for T greater than 0. There is, if we have a little bit more time in this semester, you know, we could ask the question, all right, the circuit changes at T equals 0. What happens if the circuit changes at T equals 110? Which is a very real thing. So in digital systems, you looked at square waves, right? Clock signals are square waves. So what happens when the clock goes from 0 to 1, or low to high, or however you want to say it? And, you know, whatever half a period later, it goes from high to low. And a half period later, it goes from low to high. And so that is something I used to spend more time in when I had 2-hour time blocks. And I would go over that question, how we represent them mathematically. And that's a concept called time delays. It's not very difficult per se. There's some subtleties to internalize, but that is something we can look at as well. We will not look at it. So it's just how do we write that mathematically is really the fundamental question. How do we essentially write what's a change of order? So we've been saying our circuit changes at T equals 0. What happens if it changes again at T equals 1, T equals 2, T equals 3? I suppose as a little precursor, right? One of the things I said at the start of class is you're going to see S-domain stuff in signals. And so you can look at a pulse signal that looks like this. So we can write this as 0, 1, T, and then our other axis is voltage or whatever else. That was odd. And call that 1. Anybody know how to represent that mathematically? So this ties in to what we were just talking about. It's important signal. Pulse signals are very important. So ignoring what happens here, what is this? Ignoring that. I don't care. It's a step function. But then if I ignore what happens here and ignore that that's at 1, what's this? It's a step function with an argument of a negative sign. So remember, U of T is a step function that turns on at T equals 0. U of minus T is a step function that turns off at T equals 0. So it's the value is valid for T less than 0 when it's U of minus T. That said, I can represent this with a delay. This function is V of T is U of T, there's our step function, minus U of minus T plus 1. Did I write that right? Yeah. So this is something you will do in signals. So there's a couple things going on here. The symmetry property with the minus sign and the time shift property with the other argument inside the parentheses. And I have to admit, despite having taught signals a number of times, I have to concentrate on keep track of these things. It doesn't jump out as quickly for me as differential equations was easier for me than keeping track of whether it's a +1 or a -1. but you will do this exact thing in singles, so I'm giving you a little, I guess, prep. But we're not gonna dive into delays in our transient analysis as much as we might like to. I'm sure you're very disappointed by that. So that said, it's not very neat, but it's your turn. So, oh, then let's find an eye out. Find IL of T. So, go through our process, and then you can upload it on Gradescope for our last in-class assignment. So maybe next semester, take electronics. I can turn the lights on if you want. You'll see dark. Do you like it, Marcus?
Yeah, no, actually, we use one of the 300
That's all right. In this building or in all of campus?
Why does anyone not like orange stuff Why does it have to be red?
What's the worst game on you? Is that using the halogen or not halogen? I think that's for LEDs, LED lighting more? Or the?
We all need a break after this semester.
What's that?
We all need a break after this semester.
A break?
Yes.
Anybody get any last minute internships? No one heard anything?
I still need just I'll think about getting an internship.
It's kind of like you thinking about it.
By the next semester, I'm definitely gonna be serious about internships anyway.
So as you think about your future life, I have talked to a number of companies over the last year, and many of them do their recruiting in the fall. So as you go into the summer, one of the things you absolutely should be doing is getting your resume. If you don't have your resume, you should be working on it. And use ChatGPT. I mean, there's no reason not to. There's a resume service with, AI now. I still would advise you to talk to someone who's good at this stuff. Like my sister does this for a living, this type of thing for a living. You can't talk to my sister. But certainly using ChatGPT as an initial starting point, great. Still should get a critique from someone that you're comfortable getting good feedback from. And then be ready to submit your resume as soon as the semester starts or even before the semester starts. I talked to GE at the career fair. I don't know if anybody talks to them at their booth. They do their hiring in September. So a lot of companies with established internship programs do their hiring in the fall. You will want to come in swinging because you really want an internship your third year. I mean, it's a goal. Not everybody in their third year got one, but quite a few students did. It essentially makes your graduating situation better because a lot of times it things go well with the internship, they'll give you an offer. And then you're you're starting your senior year with a job and you can be as lackadaisical as you want, without failing. Getting bad grades is always bad, failing is awful. I have unfortunately failed students in the last semester. So is other faculty here in healthcare. You can have senioritis up to a point, but that's 2 years away for you, so not immediate concern. I never encourage getting bad grades. You never know when you want to go to graduate school, those type of things. 5 years from now, no one's gonna care about your grades. In the short term, it matters. Yeah.
They're going to care about what you learn.
Well, so it depends, it really depends on the company that you're interviewing with. So some of them have very rigorous technical interviews. Like I've had a lot of students who apply to electronics companies tell me that they get questions from the introduction to electronics class. Well, transistor questions and things like that. Yeah. I mean, they'll only ask you that if you in the class or take you in the class. So if you're, coming out of circuits and you're like, well, what do you know about MOSFETs? Like, well, I haven't taken the class yet. I mean, you can always read stuff on your own, but. Yeah, we do FETs and BJCs. We start with op amps, then do diodes, and then FETs and BJCs. We do it from amplifier circuit point of view, as opposed to a digital circuit. There is some crossover analysis, but don't have time to do digital circuits anymore. May I have a question? Question on the assignment? I'm gonna use the Laplace here. You don't have to, not with the initial condition stuff. Using Laplace, so. To our steps, let's tap our steps. So that's not remember you need the Laplace transform of the source. So what's the Laplace transform of point O2 U of t? Over X. Yeah, we're done. I mean, I can always give you more work if you want. Like I said, I can give you homework also.
Just
I mean, if it counts towards extra credit for, next semester's coursework, I would mind.
We can continue to do homework 2 weeks. Give you a break for the Fourth of July. That'd be fun. I don't know. Did we have a holiday party this year? Is it?
There is, but that's more like the teachers get together, they have to go buy their thing, it doesn't serve up food for some reason. I don't
Oh, I
know why.
didn't even get emails, I guess since I never signed up, they stopped sending me emails, so I'll take the. It's at night, right? It's like,
Yeah,
it goes
it's
to
like,
10 PM or something?
either like 7:30 or 8, and usually when it starts, it's in front of the small fountain in front of the CC's, which is why there's a ton of trash cans already just sat out there.
I never volunteered, it's not how I. That's not gonna happen, that, you know.
To be honest, the only reason I even knew it existed is because, one of my professors, the one that I took, discrete structures, she was really gung-ho about getting pics to do
Really?
that. Yeah, she was like, come see me and come through my food live, and I'm like, oh, okay, cool. I guess
I
it's
didn't,
a thing.
I didn't, there was a woman that taught these structures, this is the Russian. There's a street structure.
Yeah, I had, I think I had his name was Lee or something.
I didn't remember that. Oh.
Yeah.
OG walk, is that the one?
Yeah, that's it. Yeah, I think it was her first time teaching the course.
I didn't remember that. I'm sure students told me.
That was freshman, first freshman.
Yeah.
I can't remember what it was like.
What did you think of that class? Just in general, the content, I mean.
I mean, I feel like I didn't use almost everything I learned. It kind of felt a bit like a waste of time. And since it was her first time teaching, I don't think she was all too familiar with things. I know a lot of the people who were taking my class, basically just didn't show up because they found out you could just take attendance from the campus center without actually showing up.
Take attendance from the campus.
Yeah, so, she did one of those, like, you know, they have some
I
apps
clicked.
that also has the clicker, but like they have a digital version of that, I think.
City function.
I don't remember how it worked. I just remember that if you were, she was like, oh yes, I have it set up so that you can't check in from your room. But she forgot to notice the fact that the entire campus center uses the same Wi-Fi as the auditorium does, so you could check in with that one in class. I never did that, that class was very boring, but I did not do that.
We've had some conversations about the class. When you took it, you're not in digital system now, right? You took it. Did you find it helped for digital systems at all?
Not really, no.
No?
No, I mean, it was just some basic table stuff, but I feel like the material itself is pretty self-explanatory and easy to pick up on. I think my favorite part about that class is I had one, friend in that class who was a math major, who wanted a comp sci minor, so was just taking all of the, math related courses. She spent 30 minutes on her first exam trying to solve the formula they gave us.
Trying to solve the formula
They
sheet.
given, yeah, she tried to solve the formula sheet, it was great. After 30 minutes of the class, it's like, you know you don't have to do that, right?
See you on Friday. So don't forget to take a picture and upload it. Can I close this, or is anybody looking at anything on the screen? Everybody good?